So as we started discussing in the last video, an atom, which was originally thought of as being indivisible, that's kind of like what its definition was, in that it was supposed to be the smallest unit of an element where you cannot further divide it and have all of its same properties be the same. And so it kind of is indivisible. But an atom is now considered to be the smallest unit of a given element. So this is like the most basic form of matter that consists of only one type of atom. Now, you may have heard that there are different types of what we call subatomic particles. So subatomic particles make up the atom. So it kind of is divisible, but they don't exist as elements or atoms by themselves. Okay, so that's sort of the distinction between those two. Some of you may be very familiar with this. Others may not have heard this before. So I just want to make sure that we're all on the same page if you are not familiar with very much chemistry. So there are 3 subatomic units in an element. We have protons, neutrons, and electrons. And you may have seen a very simplified version of what an atom looks like. And so I've sort of drawn that type of thing over here. Here's the thing, that doesn't really exist, but for the purposes of this class, for right now, what we need to look at is like the very basics of an atom. Let's consider that that's sort of what's going on. So on the inside of an atom, we have what's known as a nucleus. So a nucleus is something that is like the hard center heart of the atom. This is where protons and neutrons are going to live, okay? I'm sorry, my handwriting is really bad, but I've also found that when I type notes, it doesn't seem to stick with people as well. So please feel free to rewrite your own notes. But the nucleus is like where this hard mass is of the entire atom. So why do we know that? Well, there's a lot of experiments that actually took place in order to sort of figure out what atoms sort of look like. And originally we thought that protons and neutrons are sort of scattered along the entire atom. And several tests that we ran actually didn't show that at all. It showed that there's this one tiny, really, really hard area inside of the atom. And so that's what we now know is where the protons and neutrons are. But most of the atom is just air, like not even air. It's like empty space. And we'll talk about that more next week. But on the outside of an atom, we have electron shells. So it may not be just one electron shell. You may have many different types of those. So there may be very many circles, but again, that's a simplification. They're not necessarily circles, but we'll talk about that later. So that's where electrons reside. And it's actually quite a distance away from where the nucleus is. So protons and neutrons is like where the mass is of an atom. It's in the center, it's in the nucleus. And outside the nucleus, we have these electron shells. Okay, so what makes those electrons stick to things? You may already know the answer, but if you don't, protons have a positive charge to them. So proton, it kind of sounds like pro, positive, right? Electrons have a negative charge to them. So it's kind of just electricity. One is a positive charge, one is a negative charge, and just like magnets stick together, that's what makes these stick together. And that's what keeps the world sort of being in balance, if you want to consider it that way. Okay, so back to those subatomic particles. Well, so we said that those are the things that make up an element. Well, mostly that's true, but things can kind of actually differ. And so what I mean by that is that when it comes to a given element, what defines that particular element is the number of protons it has. If you change the number of neutrons, we refer to this as an isomer. And that's totally possible. If we change the number of electrons, that's what gives different types of elements charge. This is what we refer to as an ion. I don't know why both of those start with an I, but they do. And so we can change the number of neutrons, we can change the number of electrons, but what defines the element is its number of protons. And that's something to sort of keep in mind as we move forward. Okay? So let's look at another little chart that I made here. When we're looking at protons, neutrons, and electrons, it's important to know their nucleus or their location, their charge, and their mass. Now, these are relative, okay? What I mean by that is, well, so we consider to be an electron having a charge of 0, or a mass of 0, excuse me. Electrons have a mass of 0, but that's in relation to the mass of what we consider to be a neutron and a proton being about the same. So actually, I believe that an electron is 1/1800th of the mass of a proton or a neutron. So we consider that negligible, very small in comparison to the other two. So that's something to sort of keep in mind there. Protons and neutrons, as we just said, were found inside the nucleus, and electrons are in the electron shells. And then the other thing that we didn't totally go over is the fact that when you have a proton, protons have a positive charge. Every proton has a positive charge. So if you have 5 protons, you have a charge of 5. And same thing with electrons. Electrons have a -1 charge. So if you have 5 electrons, that would be -5. And sometimes that gets a little bit hairy because you add and subtract electrons, and that can get a little bit weird because you're adding and subtracting negatives. But neutrons have a neutral charge. That's why they're named neutron, okay? Now, how can you tell what it is that you have inside a given atom? Just by seeing the periodic table. Well, when you look at the periodic table of elements and you click on one element, there are some things here that are very telling from the information that's there. So the first thing that we have is we have an atomic symbol. That is one letter. Sometimes it's more than one letter, but the first letter is capital. The following letter, or I believe there's one with letters, are lowercase. Okay, so that atomic symbol stands for something. In this case, P stands for phosphorus. And then up top, above that on the periodic table, you'll find a number. It's a whole number. That tells you what the atomic number is. Now, the atomic number is the same thing that we were talking about before. You define this atom or this element by the number of protons it has. Well, that's exactly what this is. That atomic number at the top tells us how many protons you have in a phosphorus atom. Okay. Now, the bottom portion is a number with lots of digits sometimes. So this is representative of the atomic mass. But remember how I said that we can have different numbers of neutrons in a given atom or a given element? Well, this is the average of all of them together in the entire universe. So yeah, you're going to have a decimal point there. But in a given atom, one atom, you can only have a whole number of neutrons. They can't come in like 0.34. You're not going to have less than 1. So a lot of times we need to sort of round up, round down, or, look at what we're given in a particular situation to determine what our neutron count is for that particular atom, okay? So how does that tie in more definitely to the number of protons, neutrons, and electrons? Well, the number of protons are defined by the atom, so that's the same thing as the atomic number. So in this case, that would be 15, right? If we're looking at the number of electrons, well, so for the purposes of this class, we're not going to really get into having too many positive and negative charges. What we're going to basically look at is if the number of electrons and protons are the same, that means that the atom is neutral, so there's no charge. And so basically that atomic number would be the same. Now, in some instances, you're going to have negatives and positives, but that's not really looking at the organic chemistry as much. You still have that inside you. Don't get me wrong, you got lots of that going on inside you, but we're not going to worry about that too much. So when it comes to the neutrons, we do have to pay attention here quite a bit. So the number of neutrons is kind of the atomic mass minus the atomic number. Okay, but when it comes to the atomic number, when it comes to the atomic mass, this is a number that will have a decimal point in it, right? So we need to round up, round down, or if we're actually given the atomic mass or the number of neutrons, we can figure this out. But you can't have a partial number for a number of neutrons. It has to be a whole number, okay? So let's try some examples here. So I've given you some examples here, and the first one that we're going to look at is called beryllium. I've got that highlighted up at the top here, but I don't know if I can pull this down a little bit. No, not very well. Sorry about that. Let me straighten that back out there. Just pull it way down. Okay, so beryllium from the periodic table, we can see here as well. Beryllium has an atomic number of 4. So just like we were sort of saying before, is that beryllium will have 4 protons. And since it's neutral, it will also have 4 electrons. Since we're taking this from the periodic table, and the average mass is 9.01, then to figure out the number of neutrons, keeping in mind that neutrons and protons added together will give you the overall atomic mass, we could say that the atomic mass, we're going to round that up to 9 and subtract out the atomic number, which gives me 5 neutrons, okay? And that's sort of how we do these. So the number of protons in chromium, which is, let me see if I can get this up here. There we go, okay. Chromium has an atomic number of 24, so that's going to give me the protons and the electrons if it's neutral. And then 52 is the atomic number here. 52 minus 24 would be 27. Okay, so there's 27 neutrons here. Next we have selenium. So Se, I got to do a few more clicks on this than I'm used to. Sorry about that. So Se has an atomic number of 34. So that's how many protons it will have. That's how many electrons it will have. And for neutrons, okay, we need to take that 78.9, round that up to 79, subtract out 34. Let's see, that gives me 45. So I have 45 neutrons there. And finally, we have neon. So neon has an atomic number of 10. So that's how many protons and electrons I'm going to have. And then we need to round down for this one because that's 0.18. So 20 minus 10 gives us 10 neutrons. So that's pretty rare that we have 3 of each of those, right? Okay, so next, I've got another example here. Let me see if I can drag this guy down for me. Okay, I got it into position here. So now we need to start looking at the periodic table instead and comparing that to sort of what we have. So there's a couple ways to look at this. One of the things that I'll just go ahead and point out now is that when you look at all of these numbers, like these atomic numbers up top, they go 1, 2, 3, 4, 5, 6, 7, 8. Oh, wait, they're all in kind of a row. So yeah, those match pretty well, and they're easy to sort of find that way. So if we look at this, we're looking for an atomic mass of 76. Well, and in addition, generally speaking, the atomic mass will also increase about the same way. So if I'm looking for something with a symbol of AS, then I come over here and I say, okay, well, there's AS. That is arsenic. So that's what the name is, arsenic. You may have heard of that. So the atomic number up top is 33. So we say that's 33 protons and electrons. Well, now in this case, it's not the same thing as just averaging up from the number that's there, because the number that says on the bottom is 74.9. But in this example, it's telling us what the atomic mass is of this particular atom that we're looking at. So we use that. And so instead of using 75, we use 76 minus 33. And that will give us 43. So that's where that number comes from. It's the 76 minus the 33. Okay. I hope that one made sense. Next we have iron. And iron can be tricky to find. Iron is right here. So that's part of the reason why I use this as an example, just to show you that it doesn't always make sense as to what the symbol is. It does if you look through, different languages and that type of thing, but that's where Fe is iron. So the symbol here would be Fe. And we know that the atomic number is that of 26. So that tells us we have 26 protons and 26 electrons since it's neutral. And then the same way that we were sort of dealing with atomic mass backwards before, we've now got to reverse engineer that, because the number of protons plus the number of neutrons tells us what our atomic mass is. And that's where we can get 56. Okay. So there's different ways to sort of figure this out. Next we have PT. Some of you may be familiar with this as platinum. So platinum. Okay. The atomic mass is 195. That's big. Well, protons, we have 78 protons, 78 electrons, and we would have 195 minus 78 neutrons, and that is 117 neutrons. Okay. Last, we have an example with 13 protons and 14 neutrons. Oh, goodness. Okay, well, let's think about this. If the protons define which atom we have here, if that's number 13, then I just look for that number here, and that would give us aluminum. Unless you're British, well, you may pronounce that aluminium. Okay, so if we've got 13 protons and it's neutral, that's going to be 13 electrons. The atomic mass would be protons plus neutrons. So 13 plus 14 would give us 27. And the symbol is simply AO. So you sort of have to think your way through some of these. Totally possible to do though. I hope that makes sense. Let me know if you have any questions. I'm happy to help. Thanks.